You've already learned how to find the measure of center, specifically finding the mean, median, or mode. We're going to concentrate mostly on the mean and median going forward. But in interesting scenarios, it seems like the measure of center might not just be enough in terms of describing data. I'll give you an example. Suppose you have a data set consisting of the numbers 1, 12, 14, 16, and 27. Call that data set 1. And data set 2 will be 12, 13, 14, 15, and 16. So when you look at these two data sets, something very interesting occurs here. First of all, very easy to find the median as it's the middle value. So the median for both data sets is clearly going to be 14. If we're considering this to be a sample, then it turns out that the sample mean for each of these, in other words, add them up, divide by 5, also ends up being 14 for each of them. So as you can see, trying to describe this data, we end up with an interesting result. Not necessarily that the median and the mean are the same, but the medians and means are the same for each data set. But when you look at the data set itself, the data sets are incredibly different. We have this 12 to 16, whereas this goes from 1 to 27. So it's just not enough to use a measure of center to truly describe a data set to an individual so that they know that they're different, let's say. In this section, you are introduced to measures of dispersion, or in other words, measures of spread. If you look at these two data sets, while they are not different in terms of measures of center in any way, they are different in terms of how the data is spread out. Okay, one measure of dispersion is called the range. The range is defined as the max value, or the highest valued observation minus the lowest valued observation, the min. So the range for our first data set is going to be 27 minus 1, or 26. And the range for our second data set is going to be 16 minus 12, which is 4. Clearly, this ends up being a pretty good measure to tack on to the measure of center, because not only do we get the center value, but we also get an idea of how much the data is dispersed or spread out. Okay, so we obviously have one measure of dispersion called the range. There is one issue with the range, though. If you're only using the max value minus the min value, you might get a misleading representation of how spread the data is in a particular data set. So why exactly is that? Well, you know from the previous section that extreme observations can occur in a data set. You could have, let's say, hundreds of data points that are all in a similar range to each other, but then you could have one enormous number, could be there by error or just happenstance, that could be the max value. And if you throw that into the range formula, then you're going to get a misleading idea of what the true measure of dispersion is for the majority of the data. So basically the summary is we absolutely use the range in statistics, but we just are very careful when it comes to using it in advanced statistical analysis. Okay, so let's move on to yet another measure of dispersion, and we call this the sample standard deviation. Okay, the sample standard deviation is a measure of dispersion that, instead of using only two parts of the data, it takes into account every single observation in the data set. The formula for the sample standard deviation, well, first of all, S represents our sample standard deviation itself, and it is equal to the following: the square root, the sum of all xi minus x bar squared over n minus 1. This is probably our first very crazy looking formula, but just like I mentioned the other day, the whole point of showing you the formula for a sample mean is to get you used to the terminology and symbolism that goes with many statistical formulas. For example, you probably heard me say it already, we now know that this means sum of. Okay, we already know that this is the sample size. Okay, this guy right here is each observation. Recall that when there's a subscript like that next to your variable, that means you're going to be putting a number of different observations into that and rotate through and do the calculations. And the only thing left is this guy right here, but you've already learned right here that that is the actual sample mean. So an interesting first observation about this is that in order to calculate the sample standard deviation, we actually need the sample mean first. Okay, so for this problem, our example is going to focus in on the 5 members of a starting basketball team. Okay, so that usually means point guard, shooting guard, small forward, power forward, center type of situation. You can see right here that that's what we have set up. The feet and inches values, which we are very familiar with right here, those are there for us to observe. But the reality is, in order to do the math itself, we're going to concentrate on just the inches measurements right here. Okay, so getting started, clearly here we needed the sample mean. So the first thing we're going to do is we're going to find that. So remember, the sample mean x bar is equal to the sum of all the individual observations divided by the sample size. If we do that, then we just have to add up our 5 heights in inches, and we have to divide by how many there are, which is 5, and that is going to give us 75 as our result. Okay, that is going to be an important value that we're going to have to use throughout the process. Okay, one small note before we get started with our calculation. In this formula right here, you're going to see that we have s on the left and we have a square root on the right. It turns out that if we square both sides of this formula, so this side and this side, we know that, first of all, that would result in an s squared over here. But on the right side, whenever we square a square root, the square root essentially disappears. That's not the mathematical way, but that is the layman's terms way. So if that happens, then all we're going to be left with is what's inside the square root, which is this. Now, it turns out that this right here is called, I'll put it on this side, s squared is called the sample variance. Okay, the sample variance is another measure of spread, but it's just not as useful in terms of analysis, but it's something that you should know in terms of the course. So the variance is always going to be the standard deviation squared is the best way to put it, and vice versa. So I'll put a little bubble around this so you have that note. And we'll start with the example. All right, so let's get to our example where we want to find the standard deviation of our heights for these basketball team players. So it turns out that in statistics, we often use tables in order to organize information and compute larger formulas. So what exactly does that mean? So we're going to create columns that represent certain things from our data set. For example, we're going to start with our height, which we know as our xi in our formula. So we're going to create a column, 72, 73, our 276, and our 78. We now need to use this table in order to effectively calculate this right here. Now note, we already know what n is in this problem, sample size, which is 5. We could plug that in right now, but we're not going to, because we need to find this measure of this purple highlighted value, the sum of xi minus x bar squared. Right now, all we have is each one of our xi's, and we have our x bar, but we have to put that together in some computation. What I usually suggest to students, when you see a summation, then there's a good chance you're going to use a table, and always work from the inside out. So if you look at this purple highlighted value right here, the inside right now is xi minus x bar. That would be our next column. Okay, so what does xi minus x bar mean? Well, it looks like we're going to be taking each one of our observations here. So in other words, each one of our heights, our xi's, and we're going to be subtracting the mean from it. So remember, a reminder here, we know what the mean is. That's not going to change. That's 75 no matter what. So we're trying to find how far our heights are from our mean. That is our goal. So let's do that. We're going to take our first height, 72, and we're going to subtract our mean, and we're going to get -3. So basically, the height, 72, is 3 inches lower than the mean. We're going to do the same thing for all of them. Our next height is 2 inches below the mean. Our next two, which are the same number, are going to be 1 inch each above the mean. And our last height is going to be 3 inches above the mean. So effectively, what we've done is we have found values that represent how dispersed the data is between below and above the mean. Some students in the beginning will often ask me, like, well, why don't we just use these numbers as our values that we need? And let's just for argument's sake say, let's sum them up. Well, if we do sum up these numbers, we're going to get 0. As a matter of fact, we're always going to get 0 in a basic standard deviation calculation like this for this column. It's just the way the formula works, which means clearly the sum of these dispersions from the mean are not going to do anything for us. We're always going to get 0, which means we statisticians and we end up having to do something else. Well, if you look in the formula, that something else is clearly squaring the numbers. Now, squaring the numbers makes a lot of sense because whenever you square a positive or negative number, they become positive. And be very careful when you're doing your calculations because sometimes with calculators, you don't always get what you expect. I'll cover that in 1 second. But our next column here is we need to square each one of the values in this column. So therefore, -3 squared is +9. -2 squared is +4, and so forth. You got 1 squared twice, and you got 3 squared here, and you end up with 9, 4, 1, 1, and our very last one, 9. Okay, so to that tidbit that I told you I'd mention, just as an aside over here, in the calculator, if you type -3 squared, you're going to get 9. But if you type this in the calculator, you are going to get -9. Be very careful with this. Just mathematically, you should know that if you square something, it's going to become positive. But if you're just blindly typing things in the calculator and you type this right here, you're going to get a negative. It's the most common mistake students make on the first homework. The reasoning behind that, by the way, is what this right here is actually the same as saying this in mathematics, which means you are going to get 9, but you're going to end up multiplying it by -1 and getting -9. So just be very careful with this, that students make this mistake right out of the box. Okay, so once we have this column, you can clearly see that we should be taking the sum of this column. So I'm going to go over here. I'm going to take the sum of this column. We're going to add it all up, and we're going to end up with 24. So I'm going to write sum over here just to make sure when you go back you can see what it is. So basically this meant nothing. But this right here actually represents, in the formula, the purple highlighted piece. The sum of all the xi minus x bar squareds. Okay, so believe it or not, we are ready to go with using the standard deviation formula. So just to be clear, all I did was copy down this down to here. And I'm going to go ahead and find the pieces that are important here. So remember, the entire numerator right here was the point of this entire chart. And that got us to the number 24. So that is our numerator. We have 5 people on our basketball team, our sample size. So that is going to give us the square root of 24 over 4, which is the square root of 6. If we do this calculation, we are going to get 2.4, and our label is going to be inches. Okay, so we now know that our standard deviation for our problem, specifically our sample standard deviation, is going to be 2.4 inches. Just a small tidbit coming back to this. Remember that the actual expression here, which we find inside our standard deviation formula, this whole thing, is called the sample variance. So that means that this, as we worked our way down here, calculation-wise, this number 6 actually is our variance. The label for all variances are in square units, which is why we don't use the variance often when doing analysis, because the actual heights in our problem are just in inches. So how are we going to use a square inch measure to make any type of reasonable judgment? So just note, again, this is called, S squared is called the sample variance, and it's basically the number that is inside the square root before calculating it. We will get more into the meaning of standard deviation later, but generally it's loosely characterized as the average distance from the mean in a data set. This would be about 2.4 inches each way from the mean of 75, around there. But for now, it's much easier to understand standard deviation in terms of comparison. So obviously, we had this original basketball team here. So let's say we introduced another basketball team that's made up of different heights. I already did the legwork for you. I calculated the mean to be 75. So interestingly enough, the same mean as team 1, but the standard deviation is 6.2 inches. So what we're going to be doing here is we now want to compare what this means in terms of measure of dispersion. So it makes sense if we look at our first team that the heights relative to each other are not that much different. The spread, or the measure of dispersion, is pretty small. So in this case, we ended up with 2.4 inches. Now, if you look at this new team, a little bit different, right? We have a 67-inch person, 5'7", and then a 7-footer at 84 inches. So we would expect the measure of dispersion or spread between the heights to be more. And it turns out, indeed, when this is calculated, the sample standard deviation ends up being 6.2 inches, which is clearly larger than 2.4. So if we were analyzing this data, we could clearly look at these two teams and go, well, even though they have the same mean of 75 inches, clearly we're looking for a larger dispersion of heights in team 2 than our original team 1. So last thing in this section, as you already know, you've already learned about how the means of a sample and a population must have two different values or variables attached to them. Specifically, you now know that the mean of a sample is x bar, as we saw in this problem, but a population is that Greek letter mu. Now, for standard deviation, which we'll just abbreviate quickly as SD, You've just learned that the sample standard deviation is S, and that, of course, is our formula that we have been dealing with, right? Well, it turns out that if there's going to be a standard deviation of the sample, there's got to be one of the population. So we actually use the Greek letter sigma when determining the population standard deviation. Now, sigma does have its own formula associated with it. It's going to be similar to the other one, the sample version, but a little bit different. It is going to be the sum, again, of all the individual observations in the population minus, this time, mu instead of x bar, which makes sense because this is how they're paired up, but then it's going to be divided by just the population size, not -1. So we don't have to get into a lot of detail when it comes to this. I don't ask for the population standard deviation just because in statistics we tend to want the sample standard deviation for most problems. So I'm just telling you that this does exist. It often is characterized as unknown, just like mu is. So just realize that we do need a separate variable. It is called sigma for the population standard deviation. It does have a slightly different formula, but we're not going to be doing a lot of application using this formula. But just to be clear, this chart right here, big deal. Make sure you know all of these variables and what they mean.